just explainability and the outline of today. Okay, let me introduce the broad concept of machine learning. What is machine learning? That's a wonderful question today. Indeed, machine learning belongs to the broader area of artificial intelligence. And you have probably already heard about artificial intelligence a lot in these days. And what is artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. So the focus here is to mimic the human intelligence. In machine learning, we want also to give the computers the ability to learn, in particular from data, without being explicitly programmed. So algorithms of machine learning try to mimic the ability to learn of humans and also animals. And there is also another buzzword that is repeated in these days, that is deep learning. And deep learning is the subfield of machine learning that focuses on learning abstract representation through neural networks. And this abstract representation can be a potential, so can be very powerful, but also a problem from the explainability point of view, as we will see later on. So our focus is on machine learning today. And machine learning is applied in many areas today. For example, in computer vision, for face recognition on your cell phone, or image generation or object detection, and that is useful, for example, in autonomous driving, or also natural language processing. And we have seen many chatbots being proposed in the last year, or sentiment analysis, or market analysis, for example, and finally on recommender system, for example, e-commerce and social network. Our approach and the approach of algorithmic hiring in FINDHR assume that the application tracking systems make use of systems that are similar to recommender systems. So we want to recommend the candidates, the applicants, to the companies and to the specific job offers. So, what does learning mean for computers? Let me read this definition and I will comment on this. So, a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at task T as measured by P improves with experience. What does it mean? In practice, for learning, we need three ingredients. We need to define a task, we need to collect some data, so collect some experience, and define a performance measure to which we measure the improvement that we obtain in the task during learning. That's quite easy to understand if we think of how humans learn and measure also their learning. So paradigm of machine learning is supervised learning. That is what we will use today. So supervised learning means learning from the right answers. And these right answers usually are collected from the past. So for example, if we define the task of distinguishing between cats and dogs, the experience will be the collection of data with the corresponding labels that are the right answers for each data. So, for example, we can have a collection of images with each one with attached the label of dogs or cats. And we want to measure how much the algorithm is improving during time while training. And so we will measure the error in prediction, and the lesser the error, the better. Analogously, if we want to face the task of assigning a score to candidates for a job offer, then again we will have data with labels. So, for example, resumes, profiles of applicants in the past for the same job offer, to which we have assigned a score. And again, the performance measure will be the error in prediction, so the lesser the better. So, through this lecture, we will assume to have a supervised learning algorithm that has been trained for hiring. So, we will assume to have a set of data, both of profiles of candidates and job offers, a machine learning models that predicts some scores to be assigned to candidates for the job offer and to which we are interested in. And from the scores, we will derive a rank of candidates, and the top K candidates will be the ones that we interview for hiring. So we are in the screening phase of the hiring process. But this is not sufficient for us. So we don't want only the score of the candidates. We would like also to be able to ask questions to the models and to explain the models and to let the model explain himself or herself, itself, let's say. So, for example, some questions that we would like to ask to the model is why or why not or what if something different. So many questions makes us to develop different kinds of explanation methods. So let's move on and focus on what is interpretability and explainability for machine learning models. Again, another motivating example. So suppose that we have collected, like in the example before of cats and dogs, this time we have huskies and wolves with the corresponding labels, so the right answers of the supervised learning paradigm. And we ask a model to classify an image if it's an husky or a wolf one. But we obtain a misclassification, so an husky classified as wolf. And we would like to ask why this husky has been misclassified. And so we want to derive an explanation. And we can derive an explanation with a method that I will explain later. And the explanation will highlight what regions of the image is important for the model to classify as wolf. And in this case, the region of the image is the background. So we can infer that the model has a background bias. Indeed, this can be seen from the data, because if we go back to the images, we see that the wolf images have always a background of snow, while the images of the huskies have other backgrounds like the grass. So the model is learning to classify the background and not the animal that we would like to classify. And without the explanation, we cannot derive this reasoning. So we cannot investigate what is the bias, the actual bias of the model if we obtain a misclassification. So let's first of all clarify what does it mean to interpret or explain. To interpret means to provide the meaning or to explain and present in human understandable terms some concepts. And this is the dictionary definition of interpretation. But we want to distinguish between the interpretation of a model as a whole and to the explanation of a decision, of a specific decision of a model. So, for example, in the machine learning literature, interpretation is seen as a global understanding of the model. For example, if we have a model that wants to classify if a person is sick or not, the interpretation allows to find an answer to a question like which symptoms are the most common for a disease and which drugs are the most helpful. So these are questions, general questions of all the data domain, about all the data domain, while explanation will focus more on a single decision. So for example, in the same case, a question could be which symptoms determine the predicted disease for a specific patient and which drugs would work for the patient. So a specific decision is explained, while an interpretation is global. And the explanation will be provided to a human that will have different levels of knowledge. So why explainable AI? I have already introduced the motivation, but there are four main motivations that we can identify. First of all is to verify that machine learning models work as expected. And this is important in sensitive applications like the hiring process. For example, wrong or discriminatory decisions can be costly and harmful. Second, we could want to debug and improve the machine learning models. And this is very important for developers of the models, because otherwise they have not a lot of tools to improve or to debug the machine learning model. So we want to increase the amount of information derived from the same model. Third one, we would like to learn from the interpretable models, and this is important from a scientific perspective, both to make better decisions, but also to understand the world around us. For example, in healthcare, we would like to investigate the cause of medical disease like the COVID, and so learning from machine learning models can be powerful also in this case. But without explanation, we cannot really learn. We only obtain the classification, so the single output of the prediction. And finally, we want explainable AI to comply with the legislation, and the General Data Protection Regulation provides include the rights of explainability. And so we need explainable AI to comply with law. So we want to substitute the original standard machine learning pipeline that takes data, fed the machine learning model, and produce a prediction with an error, and attach an interpretability or explainability component that enable human inspection. And so also adding the human experience to the overall pipeline and the development process, so that we have verified predictions, not only predictions. So we start with the first question. I ask you to connect to WooClap like the other training session and use the code and answer this question. So the question is, what is not a direct target of an explanation of an artificial intelligence system? I will wait half a minute for your answer. So a first answer has come. Okay, let's try to move on. So clearly, it is not a target of explanation to improve the productivity of employees. It was a quite easy but also tricky question. So let's move on. And clearly, there are some challenges for explainable AI. So for example, again, in the first image here, you can see the standard pipeline, so an image, a classifier, and a prediction. And there are many possibilities to explain the model. For example, we can highlight the regions of the images that contributes positively or negatively to the prediction of a fish. For example, here the red regions contribute positively to for the prediction of the fish. And this answer to the question why you have predicted fish for this image. But we can also provide the training examples that are most influential to the prediction. So the training examples that have similar prediction to the one that we are currently inspecting, and so on and so forth. So there are many ways to explaining. And we want to provide a human-machine interaction for explanations, but we cannot answer all questions in one shot, because there are many different stakeholders. Like in case of hiring, there are the recruiters, the candidates, and so on. There are different objectives for each stakeholder, and also different levels of expertise. And developers have usually a greater level of expertise than recruiters in our case. So we need to suit the explanation to each stakeholder and to each other objective and expertise. So there are many possibilities to explain, as I mentioned before, and there is a taxonomy of explanation methods. I will try to provide you a broad view of all these explanation methods. So first of all, they are distinguished into explainable by design methods or black box explanation methods that are also called post hoc explanation methods. So first of all, we focus on explainable by design methods that are global and model specific. What examples of interpretable by design models are the class of decision trees. Decision trees are hierarchical set of rules that provides by following the path of the tree, we can go from each rule to the leaf nodes of the trees that constitutes the prediction. So, for example, here we have a tree that has been trained on data of the Titanic shipwreck. So we have all the passengers of the Titanic, and we would like to predict if a passenger has survived or not. So we take the data of the passengers and we split according to the sex of the passenger and then the class of the travel. And so we obtain, for example, if it was a female in first or second class, she will survive, would have been survived. Otherwise, in third class, a female would not have been survived. So, and this is an interpretable model if the number of decisions that we take traversing the tree is low. So if we have 100, for example, or 1,000 of decision, then the tree is no more interpretable. But this is one of the most interpretable models that we can use to provide the models by itself interpretation. A second class of models are linear models. We have again a model trained on the same dataset, and here we see that we can split the contribution of each feature of the data towards the prediction. So, for example, there are some features that contribute negatively and some others that contribute positively for the survival of passengers again. And finally, another class of models that are interpretable by design are logical rules. In this case, we have a set of conditions with the logical connectors and then an outcome. And the condition can be more than one in this case, differently from the decision tree. And so we can interpret by design these models, these three classes of models. But we cannot use only interpretable by design models because interpretable by design models usually lack of accuracy. if we see in this diagram all the possible machine learning models that there are there in the literature, we see that there is a trade-off between the accuracy and explainability. So improving the accuracy makes possible, while improving the accuracy, we can lose something in explainability. Okay, I see that in the chat they are saying that I'm not sharing the screen. Probably someone else have shared the screen before. I'm sharing again. Can you confirm in the chat that you are seeing now?
There is a question, so now they can see there is a question. Can you see the chat?
Yeah, I can see the chat.
Okay, super. And
So,
Yannick? No, okay. It was a mistake. That's okay now. Oh, no, don't worry at all. Don't worry at all. It can happen.
okay.
Don't worry. It can happen.
Okay, Yannick, thank you. So let's move on.
Sorry, I have a question actually. Can I?
Yeah, you can.
For the slide before, I just didn't really understand the model. Because why is it using the class for females and the age for males? Is there a reason? I just don't understand.
This is just an example. Suppose that you want to predict if there is some characteristic of the passengers of the Titanic that would have allowed them more to survive to the shipwreck. So this is just an example of machine learning application, and it's an example that has been used a lot in courses in the past of machine learning. So don't focus on the specific application in this case, just to understand what does a decision tree is doing. Okay, what a decision tree is doing.
It has a grounding also on this old phrase of like women and children first. That's why the people use this example and use gender, because in Titanic people say women and children first, and indeed women survived at a larger rate. Sorry.
Yeah, indeed. If you see the children, so in particular the males with an age lower than 14 years survived, the other not survived, and the females with in the upper classes survived as well. So this is just an example to understand this decision tree. I don't want to focus more on this part. So I will start again with this.
There's a comment in the chat. Okay, adult men weren't allowed on safety boats.
Okay, yeah. Yeah, that's the reason. I mean, I think I can move on because the time is running. So, and then I will devolve more time later to other questions if you have any. So, the problem with the interpretable by design models is that they are limited in accuracy, so in performance. If we want to improve the performance of the model, we need to pay something in explainability. And the most complex models like neural networks or random forest ensemble methods or other statistical models are more accurate in general than the interpretable by design models, but they are less explainable. So if we want to be accurate, we need to be able to do something also with the complex models. And so some solutions have been proposed. And the solution faced the problem of opening a black box. What is a black box for machine learning? A black box is a model whose internals are either unknown or they are uninterpretable by humans. So what we see of a black box is just the input, the output, but we don't see it inside the model. Okay, so let's do this other question, and then I will answer to some to your question in the slide. So again, on WooClap, which of the following is a transparent machine learning model that is used to build an interpretable by design explanation method? Let me also. So I see a question in the chat. The accuracy depends on the task of the model. Yes, surely. But for the most complex tasks like recommender systems, like computer vision, natural language processing, the performance really rely on the complexity of the model often. So also for hiring, it is true. Okay, let's see the results. I think that was an easy question. So a decision tree with a limited depth is a transparent machine learning model, as I discussed before. So let's move on. Recall that now we will focus on explaining black box models. So we can distinguish into model-specific or model-agnostic explanations. Here you can see above the standard machine learning pipeline again. So we have a data set, a black box model that we will indicate as B, the prediction, that is Y, and then the user. And we want to give the user something more than Y, so than the prediction. So we attach an explanation method F that will be fed with both the black box and the input. So there are two cases. One is that the explanation is model dependent, so it's specific for the black box model. And the other one is that the explanation is model independent. So see the black box, but only through the prediction. And there are various methods, both specific and agnostic, for explaining. There are also another distinction that is on the kind of data type that we are dealing with. So there are explanations that are data specific or data agnostic. For example, explanation specific for tabular data, images, or text. Others that are completely data agnostic, so that you can use whatever data type you are dealing with. Clearly, data specific usually are better for explaining a model. Okay, so let's now, I have explained the intrinsic explainability. Let's now move on the post-hoc explainability and on the global post-hoc explainability. So we want to explain a model. So we have, again, a black box whose internals are not known or uninterpretable. And we have something that is very complex, millions of parameters or billions of parameters. And so we want, again, to globally explain on all the data domain the model. So we attach an interpretable global predictor that provides us some clue of the reasoning behind the black box. And a method to extract this interpretable global predictor is to mimic the black box. So we produce a surrogate model. In practice, we train another model that is interpretable by design, for example, a decision tree again, on a training set that is built on the original data and the prediction of the black box. There are many ways to generate this data set with the separate data set, random sampling, and so on. But a clear metric, we have a clear matrix of the quality of the explanation that we can derive. That is the fidelity. So how much the surrogate model is accurate compared to the original black box model on the test set. This is the quality of explanations. So, attention check, what is the fidelity of an interpretation method? Sorry. Okay. Again, you can answer. Okay, let's move on. And I see that you are still answering. Let's move on now. So, the accuracy of a surrogate model providing a global understanding of a black box. That's the fidelity. So how much the surrogate model, so the interpretable by design model, is as a fidelity property with respect to original black box. Okay, let's move on. And an example of global explanation, so interpretation, is to explain, for example, a complex model like a neural networks with a decision tree classifier. And we can see that this is a quite famous model, an old explanation method of 1996. And I will not deal with the details of the algorithm, but you can see that the training is built on the prediction of the black box. So we will query the black box to obtain other answers from it, and then train another model that is interpretable by design. We will obtain this kind of explanation that is, in this case, quite long, but at least is better than a single prediction. There are other methods to derive a global understanding of the model. So, for example, we can permutate the features of the original model and see how much the accuracy of the black box decreased, and this will be a measure of the feature importance. So the actual decrease is a proxy to say that the feature that makes possible the decrease is quite important for the prediction of the black box. And there are also other global interpretation methods, and I will not deal with the details on this, but I want you to understand that there are various possibilities that can be employed to explain globally a black box model. Now, let's move on and go on the local explanations. And for local explanations, we will have a single instance to which we focus and to which we want to provide explanation. So we will...
Antonio, there is a question.
Yeah, just this slide, and then I'll ask
okay.
Okay. Okay, so let's put us in this situation. We have a candidate. So, and for this, the explanation is local. So we have a specific candidate with some years of experience, an education level, the capability of problem solving, and so on. We have a black box, and we have a predicted outcome by the black box that is not admitted to the interview with a certain probability. So we can ask some questions. For example, why this prediction, or why not another prediction, or what if I change something in the candidate? I assume to have another candidate and ask the black box to predict as well to this other candidate. So first of all, we will focus on why a given prediction. But before moving on, and before doing also a break, I want to answer to the question. So the question is, does the fidelity will never be 100% since it is based off a surrogate model? And the answer is yes. So if you train a simplified model like a decision tree or on the data of more complex models, you will lose something in the quality of the prediction. And the fidelity measure exactly this. So how much is the quality of the prediction? I hope I have answered this question. Let us see what is the most difficult question. the most difficult description. So describe what features of the instance determine the current prediction. This has been connected to why not. Indeed, instead, this is a why question. So why do you have predicted this data with this class? That's, if you think about the wolves and ASCII example, then the features of the instance are the background pixels. And so in this case, you are asking why have you predicted wolves? And in this case, the answer is because I'm looking at the background. So this is a why question more than a why not question. So let's move on. And so prototypical explanation are another method to answer to the question why. And for example, we have we can give provide to the user other candidates in case of hiring that have not been admitted to the interview. And so we want to find similar data, similar candidates, similar instances that has the same outcome. And similar means close in some distance metric. And for example, here you can see that the other prototypical examples have similar features in their profile, but all of them have been not selected for the interview. A second class of methods again focuses on attaching an interpretable local predictor, not global, but local predictor, to the black box and provide a set of rules or some other interpretations for the prediction. And these local models focuses again on a single prediction, and we can audit the black box around the given instance, the one that we want to explain, and learn an interpretable local predictor. And a local predictor can be, for example, also a linear model, like in this case, where we are approximating the boundary of this decision. So blue samples versus red samples, we are approximating the boundary and we are obtaining some feature importance for the actual prediction. And this is the reason behind the LIME explanation that we have already seen. So there are four main passages in this for this method. First one is a technical passage to be able to be data agnostic in some sense. So we want to map from the original data domain to an interpretable data domain. For example, in the case of images, we want to have superpixels to explain and not single pixel, because superpixels like that are collections of pixel correction regions of the images are more interpretable than single pixels. Then we will sample around the interpretable data and go back in the real domain and find it, and this will give us a collection of real data nearby the actual instance that we want to explain. And finally, we will solve a lasso problem, that is the training of a linear model with some regularization, L1 regularization, to be able to compute a set of feature importance for the actual instance that we want to explain. For example, in the case of the hiring, the screening process, sorry, we will obtain a bar plot like this one, where we can see the importance attributed to each feature of the candidate that is applying. And so there are positive influencing feature or negative influencing feature. And this clearly depends on the specific instance we are explaining. There are other methods methods to provide local explanations. For example, instead of a linear model, we could want to obtain a decision tree, a surrogate local model, or a set of logical rules that approximate again the decision boundary and that explain the actual prediction, the actual instance that we are focusing on. So there are evaluation metrics also in this case. For example, the fidelity again, that is the accuracy of the surrogate model with respect to the black box prediction, but also the faithfulness, so the correctness of explanations, and this in particular for the case of logical rules, the completeness, so the number of reasons covered, because we can also have a partial covering of the features, and the comprehensibility, so the difficulty, the cognitive effort for the human, because the human is the subject of the explanation. We want to be that the human will be able to understand the actual explanation. Then also the succinctness, so how much is synthetic, compact, the explanation. And finally, the stability. The stability means that if we have a similar instance that we want to explain, then the explanation should be similar. And you can see here, for example, if we explain a nearby instance on the same data domain to the one that we have already explained, we expect to obtain a plot, a bar plot, so a feature importance that is similar to the original one. There are other methods again to solve this local explanation problem. So, and again, we are answering the question why. So, what is the variable contribution to the prediction? And we can obtain also breakdown plots. So we want to decompose the prediction into contribution that then, if added, give us the actual prediction. So for example, we can have a model F, that and we want to decompose this model into some contribution that are indicated with the letter B. So B0 will be a base contribution, and then all the other features will add some contribution or subtract some contribution. And a method to obtain this contribution is to add one by one each feature to the model. So we enable the model one by one to use the single feature. But this is quite arbitrary, because we need to choose the order to which the explanatory variables are inserted, are made available to the black box model. So there is a famous method that is called SHAP, that means Shapley additive explanations, that is inspired by the coalitional game theory literature. And in practice, the Shapley value, the SHAP value, is the average marginal contribution of a feature value across all possible orderings that we have seen before, that constitutes coalitions. And so the formula to compute this Shapley value can be quite complex, but in reality, we have simply the contribution of a single feature, that is this delta value here, that is simply the variation of the prediction when I add a single feature, like the J feature in this case, and then the contribution to the model of the feature J will be the average over all the orderings. And the average is this complex expression here with the factorial. But in practice, we are simply doing an average of the contribution of all the orderings. And because we have orderings, The problem is that this method is inefficient and is very slow to be computed. But there are efficient approximation algorithms that exist, for example, for decision trees. You will see in the exercise, in the data exercise in 2 weeks, the data analysis sessions, examples of applications of this SHAP algorithm for explanation. And this is quite an industrial standard now, so it's quite famous in the application, also on the hiring process. But let me explain better what are Shapley values. And I will help myself with an example. So suppose that you want to predict the price of an apartment. And in this case, there are 3 main features you are evaluating. The first one is the area of the apartments, like 50 square meters, and located in the 2nd floor. The second is the presence of a park. And the third one is if cats are banned or not in the nearby. And so you want to change these, you want to evaluate the contribution of a single feature, like the presence of the 1st floor, the apartment being in the 1st floor instead of the 2nd, and to then evaluate the outcome, the predicted outcome of your model. So while before the prediction was 300,000 euros, now is 310,000 euros. So this contribution, this change, the change in the original, in the data features, has make the prediction also change. And measuring these, the change in the outcome, we can evaluate the contribution of a single feature. But in the case of tabular data, like in the screening process, we need to be able to substitute the presence or absence of a single feature in our data. And so we need, like in the LIME algorithm, to substitute some feature value when we simulate the absence of the features. So for example, if we have this feature vector here that include the age, the weight, and the color of some data that abstract data, let's say, and we want to substitute and simulate the absence of the weight features and the color features, we need to establish some reference value to be substituted in the alternative data to be able to compute the actual contribution of each exact feature value. I know that this is quite a technical passage of the algorithm, but it's important if you want to understand the data analysis application that we will exercise on in about 2 weeks. So in the end, applying SHAP, we obtain something that is called a waterfall plot and a force plot. So in the waterfall plot, you can draw the contribution of the single features to the prediction in this way. So each feature, like the capital loss, marital status, occupation, all these are features of the original data, and they are attributed a contribution that can be negative or positive. And depending on the average value that you use as a reference value, you will end in the actual prediction. So for example, here the prediction is 0, starting from 0.4. And this summation of the contribution from the reference value, that is the V0, the contribution of the absence of all the features, will end in the actual prediction of the model on the specific instance. You can also draw another plot that is called the force plot, where there are like pushing, where each feature is pushing in a direction or in the other, like the red features are pushing in an higher model output, while the blue features are pushing in the lower direction. And in the end, the equilibrium is found at this actual model output, in this case of 24.41. I think I can do a pause now for questions if you have any. Otherwise, I will move on. Okay, no questions. Everything is clear. That's fine for me. And I'll try to move on from this. So here you obtain the waterfall plot that I have described before. And the question is, which feature is contributed the most to the output prediction? Let me enlarge this image. I know that the features are not readable. I hope you can read better on your screen.
Yeah, they can do it. They can do it, I suppose.
Okay. Okay, let's try to move on. So the correct answer is capital loss. And most of you have spotted this. And capital loss is simply the feature that has the most negative contribution, and so in absolute value is contributed the most. So let's move on. We have tried to answer the question why with the many possibilities. Now let's focus on the question why not a different prediction. And the principal method for answering these questions is counterfactual explanation, is to provide a counterfactual explanation that is a description of the smallest changes to the feature values that change the model outcome. So let's do an example again. Assume that you are applying for a mortgage in a bank, and the bank will evaluate your profile and will say to you that the application is denied. And you would like to ask the bank, what should I change in my application to get the loan granted? And so the bank, it would be great if the bank would answer you with other examples that have alternative outcome, like example where the loan has been accepted. So, for example, in this example, the bank can say, if you change your car owner property or you increase your outcome, then we will accept your application. And this explanation is related to causality. So, and the typical phrase for counterfactual explanation is, if something had not occurred, then the outcome would not have occurred. So a different outcome would have, there will be a different outcome in the application. And this example is quite similar to the screening process, because in screening you want to explain why not, for example, to candidates that have not been accepted for the interview, why they have not accepted. So give alternative examples. And this is the base of algorithmic recurse. But algorithmic recurse requires also that the change in the proposed changes in the profile of the candidate of the bank application or whatever are actionable. That means they can be effectively done by the applicants. So, for example, if I say to the candidate, you need to lower your age, this is not actionable because the candidate will not be able to do that. It's impossible. Another example is in the bank application. we can ask to increase by a real high value the income of the applicants, but this may require years, and then we could worsen other features. So the changes that we are asking to the candidates are highly costly, and so they are not actionable in the end. And there are various ways to derive a counterfactual explanation if you have a machine learning model. And clearly, in this case, the explanation is local. So the one way is to randomly change feature unless you obtain some plausible, feasible, and actionable explanation. And this clearly has high cost of computation. Another way is to try to find a counterfactual that minimizes some loss or distance from the original instance that you want to explain and ending yet in another outcome, so in the opposite outcome in the case of binary classification. So you are sampling from a plausible or feasible domain to enable explainability of the alternative features that you are proposing to the applicants. There are also, in this case, there are metrics for evaluating counterfactual explanation. I focus only on two. The first one is the speed. So you want to generate counterfactuals fast enough to deploy your explanation system in the real-world application. And the other one is the proximity. So you would want to provide explanations that are similar as possible to the original instance in order to have to minimize the cost of changing for the applicants in the case of bank or hiring process. Okay, so we have here another example. This is a quite complex example. I will leave you 2 minutes to solve this problem. So let's assume to have this decision tree. That is the surrogate model that we have seen before. And the instance that you want to explain is this one. So you have an age of 22, an income of 800, and the job is clerk. You want to provide a counterfactual explanation for the prediction. Which are the possible counterfactual explanation for this model? Okay, let's try to discuss the answer. I see that in the last seconds there are many of you that are trying to answering. Okay, let's move on. So we need to obtain an alternative prediction with respect to the instance we want to explain. So let's assume we change, let's see what is the prediction. We have an age of 22, so we go on the left, and then the income, the job is clerk, so again on the left, and the income is 800, so again on the left. So the prediction is deny. We want to provide an instance that have an alternative prediction, so grant. So if we put job clerk, we are not changing anything because the original instance is job clerk. If we put job other, then we end up in other branch, and then the age will be greater than 17, and so we obtain a grant. So this is a possible counterfactual explanation. The other one are similar. Let me just check the income 100. So we have age again 22. And in this case, the income is not 800, but 1,000. Sorry, not 100, 1,000. And so we go on the other side, and so we obtain again a grant. The other cases are similar. So if you traverse the decision tree, you obtain the same prediction. Okay, let's move on. And so the final question we can ask to the model is what if? And what if means that we can vary a single feature and look at the prediction of the model and see what is the profile of the prediction if we keep the other features at the same level. So for example, in this case, in this plot on the left, we can see that changing the age from 50, about 50, going on the left, so lowering the age, the model response is quite increasing, so it's almost monotonically increasing. And this provides us another view on the explanation. So what if the age is changed? Then the model response would have changed as well with the corresponding value. And on the right, another examples on communication skills if you are doing an automatic screening process. Clearly, there are some counts that are, if the variables are correlated, then you cannot disentangle the changing of a single feature with the other features. And there can be many variables to inspect. And so you have still a real complex explanation that is not really understandable. You can also aggregate, so change multiple features at time, so you obtain the so-called partial dependency plots. So you change some features, a subset of features, and keep the others fixed, and you obtain again a profile. Here we are changing only age, but also not only age, but also the other features that are dependent on age. And so by averaging on that, we obtain another profile on the model response. And if we aggregate the partial dependency plot on all the instances, we obtain an average, and this is called the individual conditional expectation that provides us a more global view over the prediction and the model. So I'll move on by showing you just two examples of explanations on data that are not tabular, but images and text. I will skip the time series. So in the case of image data, we can obtain an explanation that is a saliency map. That means that we are highlighting the pixels that are mostly contributing to the prediction. And there are two methods to creating a saliency map. The first one is to assign to a single pixel a saliency value, so an importance, and then to draw this saliency value with colors. And the second one is just to aggregate pixels into pixel groups that are called superpixels. And we have seen an example in the wolf versus ASCII's example at the beginning. So we have the superpixels, and we aggregate superpixels to obtain, again, mapping of feature importance. The part of the image that are mostly contributing to the prediction or are decreasing the outcome of the model response. For textual data is quite the same, so we will have some highlighting of the words that are mostly contributing or least contributing to the prediction. And so, for example, in sentiment analysis, an analysis like that of the negative or positive words is very important to understanding the prediction of a model. So now we can focus on recommendation and rankings that are the models that are used in the hiring application. And we can inherit from the general overview some explanation methods, like a post-hoc explanation method, again, like feature attribution or counterfactual examples, and also interpretable by design models that are explainable architecture or rational-based models that I have not introduced before, but I will introduce now. And finally, we have also other ranking properties that we can leverage to develop some other explanation. I will not cover this one because I think you have already a lot of materials to work on. So, about the post-hoc explanation, clearly we cannot apply post-hoc explanation like they are on ranking, but we need to convert the ranking problem into a classification problem before. So, for example, we have the top K items for hiring the top K people that will go to the interview, and we can transform the problem into this binary classification problem to be inside or outside the top K. And so again, we have feature important methods like lime or sharp, or also counterfactual examples. And for counterfactual examples, we would suggest the candidate how to modify their profiles to promote, to go, for example, inside the top K if he or she is outside the top K, or demote outside the top K if it's inside. And these provide alternative, let's say, candidates, alternative profiles that are explanation both for candidates and for recruiters. So, attention check here. How can you apply a feature importance method to a ranking algorithm for a top K element selection? Okay, it's time to move on for the last part. So here there are many errors. Okay, so the question is on feature importance method, so not counterfactual example. And to provide a feature importance method, we need to convert the problem into a classification problem top K versus out of top K. So the providing a prototypical, so the second answer, the answer number 2, is more is not a feature importance, but it's a prototype-based explanation. And feature importance is more like, as I mentioned, lime or sharp. So you will obtain something like, something like this. So a decomposition of the prediction into some variable importance. We can move on. There are interpretable by architecture models that are used in ranking, and other than decision tree that you have seen already, we can use generalized additive models that are another class of models that can be applies a function to each separate feature, and then the outcome, the output of each function that deals with the single features are aggregated in an additive way to provide the actual prediction. I will not ask a question on these, just for your, let's say, background culture. And finally, this is quite important instead, and also novel, there are rational-based or concept-based models. In this case, we are concatenating a model that is learning abstract representation of actual data instance. For example, the characteristic of some images, like or some animals, again, long tail, for example, you can see. So in the first part, we are extracting the so-called concept that are feature that then an interpretable by design label predictor can use to provide the final prediction. And in this way, the interpretability of the model rely on the concept that have been extracted from the concept encoder model. So we have a first part that can be also uninterpretable, black box, and the second part that is interpretable. Okay, I think I will skip this question because of time. Probably if we have time, we will go back to the question. And I want to focus more on our approach to explainability in HR selection, and in particular, the screening phase of the HR selection. Clearly, this is a work in progress, so our project is as another year, and so I will present partial results of our work. First of all, we have mapped the stakeholders, and we have distinguished the stakeholders into internal or external with respect to the application tracking system that is used, and also primary, secondary, and tertiary. And in this mapping, we can distinguish between several groups of stakeholders. The first one are clearly the candidates that are primarily involved in the selection. Then there are recruiters that are both internal or external if they are consultants. Then auditors, external and internal again, and finally developers. Clearly, each stakeholders wants a tailored explanation, and so we need to vary the explanation according to the objective, the objective stakeholder. We have designed a general pipeline for the screening process. So assume to have, as I mentioned in the beginning, a set of data that are job requirements and candidate profiles. And so we obtain here a matching function. We need to pass through a matching function that matches the characteristics, the properties required by the job offer and the profiles of the candidates. And so we obtain a fitness matrix. And by obtaining the fitness matrix, we complete the preprocessing. And you will see an example of this pipeline and of the preprocessing in the data analysis exercise. Then, after we obtain a fitness matrix, we need to fit a model that can be a black box model, an interpretable by design model, and so whatever is the best for our application. And we obtain the score. And again, from the score, the top K of the candidates. We can also explain the score, as I mentioned before, and assume that we want to explain the score with the contributions, like, for example, with SHAP. Clearly, other explanations are possible. So in the final phase, we obtain and we analyze the ranking, and we try to obtain also and design an explanation. So we distinguish three clear data domains. The first one is the human understandable data domain that comprise the candidate and job offer data. The second one is the feature engineering data domain, where we have fitness values that can be binary values, float values, so they are less interpretable than the original descriptions of job offers of our candidates. And finally, we have the ranking output data domain, where we want to also include the explanation. We also provide a method to include some metadata optionally for the description, the profiles, and the job offers. And these are JSON schema that helps explaining the matching process in the feature engineering part of the pipeline. And so in this metadata, we can have information about the type of the attribute, like ordinal, numerical, or categorical, and also the usage. And this is quite important for privacy, if the attribute provided by the candidates are sensitive, or for fairness, if we want to use some principled way to provide more fair rankings and also explanations of the rankings. So the metadata description allows to explain the first part of the preprocessing if we have access to the matching function. But we can, depending on the stakeholder, on the application, we can have different frameworks for explanation. The first one is the most easier, but also the one with least information, that is the black box framework. In this case, we have not access to, we cannot access to the preprocessing, and the model is unknown. So the explanation needs to be model agnostic, and we have a one-step explanation directly from the ranking outcome data domain to the human understandable data domain. But we can have also other frameworks depending on the stakeholder. We can have a gray box framework. In this case, only the machine learning model is a black box, while the preprocessing is accessible, and we have also the metadata. So the explanation needs to be model agnostic only for the part of machine learning model. But then we can design a two-step explanation that first goes to the feature engineering domain, and then go back by the inverse transform of the matching functions. And finally, we can have a completely white box framework where also the machine learning model is interpretable. For example, the now famous decision tree. And so in this case, both the preprocessing and the model are accessible, and the explanation can be model specific and global, model specific in particular, and the explanation of the model is inherited from the interpretable model. So again, in this case, we have a two-step explanation where the first step is provided directly from the by the interpretable model. So summarizing, what are the questions for explanations? So I have summarized before the question as why not, and what if. So what are the questions that recruiters usually ask to the model? Clearly, if you want to contribute to this project, you can if you have other questions in mind. Typical questions are about transparency. So for example, what features are the one used by the model, and how much they weight, how much the feature weight. And for example, we can have a greater weight attributed to the experience compared to the weight attributed to education. Then we could inspect the ranking. So the recruiter could also inspect the ranking. So for example, asking the question, what if a candidate changes its application? And finally, also verify the description, the requirements of the job. Is it flawless or not? Clearly, there are other questions that the recruiter can ask to the model. And also the candidates can ask other questions, for example, about the transparency, what are the most important features for the ranking, or the weaknesses and strengths of the CV. And also about actionability, using counterfactual explanation, the candidate can ask, what should I change in my application to improve my ranking? And finally, for auditors, about the general behavior of the model, about fairness, bias, and privacy. So, for example, how does the model behave in front of intersectional candidates, or make use of the model? Does the model make use of protected features, or similar candidates are evaluated similarly? I see a question about flawless. So the flawless can be, I can think about an example. For example, I can ask that the age of the candidate is too low to obtain a certain degree. This is inconsistency in the job. I can ask by mistake. I mean, the recruiter can compile the job offer putting an age that is 15 years instead of 35 without paying attention to it. And then after the screening, they can investigate why the screening is the outcome of the screening is in some way, and then inspect the job offer description, the feature of the job offer, and so be able to spot some flow in the job offer. This is clearly a very extreme example, but just to make you understand what we intend for verify a job description. I hope to have answered, Maria. Let me just conclude, and then I will leave you space for other questions, also general questions that I have seen in the chat. So, in the concluding, explanation are a powerful tool to open the black box, because black box are very powerful from the point of view of performance, accuracy of their prediction, but they are not, they cannot, they do not allow to interact with the humans, with the user. And explanation comes in many different forms, depending on requirements, questions, and stakeholder also, and help to enforce anti-discrimination and fairness and counteract biases, should be tailored to the specific needs of stakeholders involved, in particular in the screening process, hiring process, and so on. So we have left also some other reference of books for explainability that are quite recent, and that's the end of my presentation. I have been in time. I'm very surprised of this. And thank you for your attention.